Hello, everyone. Today, our group will present our project on fine-tuning models for dialogue summarization. Our focus is on using several advanced fine-tuning methods on different base models to improve summarization performance. Now let's take a look at the project background. The goal of this project is to summarize the text using the Llama model. Then the original model is fine-tuned using 3 different methods, and these methods are compared. The full name of the Llama model is Large Language Model Meta AI, which is a series of open-source large language models developed by Meta. It is a model created based on transformer decoder only. This model is suitable for tasks such as text generation, summary generation, and chatbots. The 3 fine-tuning methods used in this project are QLoRa, prefix fine-tuning, and prompt tuning. These fine-tuning methods are very commonly used methods. They can save resources and generalize the model. This is an example of a text summary. The text summarization task will be as follows: input some dialogues and finally output a sentence or paragraph summarizing the whole content. In the next part, we will introduce some basic technique ideas of our fine-tuning methods. The first one, prefix tuning. Prefix tuning equips the model with a cognitive guide. We prepend 20 trainable vectors to each transformer layer, essentially giving the AI a contextual prompt. Prefix tuning adds a set of learnable key-value pairs to the self-attention layer in each transformer. During training, only optimize these prefix parameters while keeping the original model frozen. The prefixes serve as additional input embeddings and participate in the attention mechanism computation. Next, let's understand what prompt tuning is. Prompt tuning changes model behavior by learning soft prompts at the input level. The principle of prompt tuning is to add a set of learnable virtual token before the input to guide model behavior. These virtual tokens are learned during the training process, and the model will understand the training objectives more easily through these prompts token. Code implementation of prompt tuning is divided into 4 steps. The first step is to define the prompt tuning configuration. Then adjust the training parameters and settings. The third step is to modify the way to load the fine-tuned model. The last step is to retrain. Now, let's unpack QLoRa. While LoRa inserts adapters into full precision models, QLoRa first applies 4-bit quantization to compress parameters to 1/4 size, then adds low-rank adapters. This slashes memory usage to just 1/3 of LoRa's demand. The magic lies in double quantization, 4-bit storage for efficiency, but 16-bit dequantization during computation to preserve precision. We only tweak the query and value sub-layers in attention modules, like teaching students to retrieve information differently without altering their core knowledge. And according to the original paper, over 95% of full fine-tuning performance at less than 1% of the cost. Finally, we compare our fine-tuning methods, QLoRa, prefix tuning, and prompt tuning, across key dimensions. QLoRa achieves ultra-low memory usage through 4-bit quantization, making it ideal for consumer GPUs. Prefix tuning involves more parameters and memory due to modifications at every transformer layer, while prompt tuning is the most input-efficient and CPU-friendly. Only prefix tuning alters the model's internal structure, whereas the others keep the base model intact. In terms of application, QLoRa for resource-constrained environments, prefix tuning for complex generation, and prompt tuning for simple classification. All methods are supported by Hugging Face PEFT, with QLoRa also requiring bits and bytes. However, in our first experiment, we used default parameter setting and run 3 fine-tuning methods on Llama 3 to 8B. We got very low Rouge score, indicating the fine-tuned model does not catch the key point of the dialogue. Thus we decide to do further improvement and compare different base models or change model parameters to get higher Rouge scores. We selected Llama 3 to 8B, Llama 3 to 8B and DeepSeek R1 Distill Llama 3 to 8B as our candidate base model and use QLoRa to adapt it on a single 24 GB RTX 3090. We prepared 3 datasets, 2,000 training samples to teach the model, plus 500 validation and 500 test samples for evaluation. For metrics, we used Rouge scores, which measure word overlap between AI summaries and human references, grading how closely they match. Hardware-wise, we used a 24GB RTX 3090. Let's dive into the key parameters for optimizing Q-LoRa fine-tuning, as shown in this clearly structured slide. The configuration is divided into 3 logical sections. We use the most common method to do model quantization like this. For the training process, one step means one update of parameter. We use 2000 steps because we set train batch size to 1. And the learning rate equals 0.0002 falls within the recommended 0.0001 to 0.0003 range for medium datasets, fast enough to learn but stable. This is implemented with a cosine scheduler for adaptive rate adjustment. Finally, the adapter setup. We chose rank 16 as it provides sufficient expressiveness for our task while remaining memory efficient. LoRa Alpha scales the adapter's influence, carefully balancing new learning against pre-trained knowledge. In our experiment, we evaluate the performance of Q-LoRa in model quantification. We can see that the raw Llama 3 to 8B needs 15 GB to run. But with 4-bit quantization, we shrunk the model to about 5 GB, like compressing an encyclopedia into a pocket edition while keeping all the knowledge intact. And the trainable parameters are reduced to 30%, greatly lower our computing need. In this slide show a summary test result of Llama 3 to 8B instruct. The human summary is concise and focused, but the Q-LoRa fine-tuned Llama 3 to 8B model generates a repetitive and overly long summary, with phrases like, "They all feel very happy and have a very good time," repeated. As shown in the analysis, increasing max new tokens to 200 worsens this issue. Even the original model with a lower token limit performs better in terms of coherence. Both Llama 3 to 8B and Llama 3.1-8B show similar repetition problems after fine-tuning, highlighting the need for careful tuning of generation parameters. Moving to next slide, this table shows the Rouge scores for 3 setups. Baseline Llama 3 to 8B with max new tokens set to 100 and 200, and the fine-tuned version with 200. We can see that the baseline model with a shorter generation with len equals 100 performs best overall, achieving the highest scores across all Rouge metrics. Increasing the token limit to 200 causes a drop in performance, likely due to verbosity and repetition. Fine-tuning with Q-LoRa slightly improves results over the baseline with len equals 200, but it still does not surpass the shorter baseline. This suggests that longer generations and fine-tuning need careful calibration to avoid degrading summarization quality. Furthermore, we have also tested the DeepSeek R1 distill to see if it could address some of the issues observed with Llama 3, such as repetitive summaries. Next, we show the baseline Rouge scores at DeepSeek R1 distill Llama 8B at 2 different generation lengths, 50 and 100 tokens. Interestingly, the shorter generation with len equals 50 achieves slightly better performance across all Rouge metrics, with Rouge 1 at 0.4025 and Rouge L at 0.3316. As the length increases to 100, the scores drop marginally, suggesting that concise summaries tend to be more precise. Overall, these results demonstrate that DeepSeek performs competitively even without fine-tuning, and is potentially more stable than Llama 3 in zero-shot summarization. Furthermore, this slide presents Rouge scores after fine-tuning DeepSeek R1 distill Llama 8B with different generation lengths and training steps. We observe that Rouge 1 steadily improves with more training, peaking at step 3000 with a score of 0.4244, while Rouge 2 also reaches its highest value of 0.1920 at the same step. Similarly, Rouge L and Rouge L sum both show consistent gains, with the best performance again at step 3000. These results suggest that moderate length training, particularly around 3000 steps, strikes the best balance between learning and generalization for dialogue summarization. However, beyond that point, scores slightly decline, hinting at possible overfitting. Moving this next slide, this bar chart compares Rouge scores across different configurations at DeepSeek R1 distill Llama 8B, including both baseline and fine-tuned models. We observe that fine-tuning with len equals 50 and around step equals 3000 consistently yields the best results across all metrics, Rouge 1, Rouge 2, Rouge L, and Rouge L sum. While the baseline with len equals 50 already performs well, additional training steps enhance summary quality further. Interestingly, len equals 100 tends to perform slightly worse, highlighting that a shorter output length is more effective for dialogue summarization in this setting. As you can see from the slide, across all Rouge metrics, a shorter max new token setting of 50 consistently outperforms 100, yielding gains of up to plus 0.02 in Rouge 1, Rouge 2, Rouge L, and Rouge L sum. We found that shorter generations produce more precise and relevant summaries, while longer outputs tend to become verbose or drift off topic, lowering overall Rouge recall. Based on this observation, we recommend setting max new tokens to 50 for concise and accurate dialogue summarization. This slide summarizes our analysis of fine-tuning steps. We found that step 3000 delivers the best Rouge scores across all metrics, including Rouge 1 at 0.4244, Rouge 2 at 0.1920, and Rouge L sum at 0.3456. This step appears to strike the optimal balance between learning and generalization. Beyond that, at step 4000, we observed a drop in performance, suggesting possible overfitting. However, compared to the baseline, even step 4000 still provides significant gains. Based on this, we recommend setting step equals 3000 as the stopping point for fine-tuning to maximize performance while avoiding degradation. Well, we have already introduced all of our work. Through this project, we experimented with 3 fine-tuning methods: prefix tuning, prompt tuning, and QLoRa on a base model for text summarization. After analyzing the subpar performance of Llama 3-8B, we switched to DeepSeek R1 and tested varying training parameters such as training steps, max new tokens to observe their impact. The project deepened our understanding of how these fine-tuning methods balance computational resources and performance, guiding model selection and parameter tuning to surpass benchmark results. Moving forward, we plan to explore more efficient fine-tuning techniques or hybrid strategies, as well as adopt comprehensive evaluation metrics beyond Rouge scores, such as human evaluation, fact consistency checks, and domain-specific adaptability tests. This experiment provided valuable insights, and we will continue refining fine-tuning strategies to enhance the model's practicality and generalization, aligning with real-world applications. Thank you for your listening.